And let me share the screen. The example here, similar to the previous one, but maybe a little more complicated. What can we see here? We have a uniform cylinder bar AB, and they give the information of the mass of AB. And AB is in the horizontal orientation, and AB is driven by the crank OA, and they give the information of alpha and omega when OA and CB are normal to AB. It means in this condition, we have the right angle between OA and AB, and the right angle between CB and AB. But what we need to find is we need to compute the force in CB. The force in CB. The force in CB. They suggest that, wow, equation 6 per 3, this one may be the summation of moment, but the suggestion is, hey, in this case, we may try to do the summation of moment about point A. It should be a good suggestion. Summation of moment about point A. So when we see this picture, from the previous derivation, I hope you can think by eye. You can think the problem not so difficult if you apply the idea of two force member. Do you think CB can be a two force member in this case? In this case, we know the mass of AB, but they didn't mention. They mentioned that the link CB can neglect the mass. And for OA, they didn't talk about the inertia property of the OA, but they tell the omega and the alpha of OA. In the previous example, they give the information of moment, and we need to think about the effect of the moment that appear on the alpha, the omega. But in this case, they give alpha and omega in this instant, but they didn't talk about the moment of inertia. So yeah, let's summarize the information from the problem. What do we have from the problem here? They give the mass of AB 0.8 kilogram, the mass of CB can be neglected. The alpha 0 and the omega 0, yeah, it's provide, no, 4 and 2 radian per second. And at this moment, OA perpendicular to AB and CB also perpendicular to AB. And what we need to find is the force in CB, the force in CB. So, okay, AB in the horizontal, CB is in vertical. We have A, we have B, and at this point we have B and C. And we don't know, seeing by eye, you can see the CB is a two force member because mass of CB is 0 and we don't have any moment apply on CB. But let's try to do it again. I mean, to prove the two force member again, to make it clear for you, to prove that CB is two force member. So at the point C, we may have CX, CY at this point. And at point B, the connection point, to make it in the equilibrium, the BX should be on the opposite, maybe, and BY on the opposite direction to CY. And which means for AB, we have the same magnitude of BX and we have BY. And something like this. But let's see the link BC. First, let's see the link BC first. The summation of force in X direction is equal to the acceleration of the center of gravity in the X direction. But the mass of the CB is 0. So the summation of Fx will be Cx subtract by Vx equal to 0 because the mass is neglected. Summation Fy equal to MAY, A of the center of gravity of the link CB. Again, mass 0. So summation Fy, we have Cy and By. And We have mg also, but mass is 0. So from the first equation, Cx equal to Bx. From the second equation, we have Cy equal to By. And for the summation of moment about point G is equal to I bar alpha, but we neglect the mass of Cb. So again, I will be 0. So the summation of moment here, we may have L per 2 and L per 2 between G and C and G and B. So counterclockwise is positive. Let's make, yeah, it's fine to make counterclockwise as positive. Counterclockwise positive means if we have the alpha in this link, alpha CB, if we have the alpha in this link, the alpha CB will be positive counterclockwise, and summation of moment by Cx and Bx, what we have is generate the clockwise moment, so minus Cx L per 2 and minus Bx L per 2 equal to I bar alpha, but I bar 0 neglect mass, so minus Cx should equal to Bx, but Cx itself also equal to Bx. So yes, by this, yeah, finally we know that the Bx equal to Cx and it need to equal to 0. And again, the link CB, the same explanation as the previous page. The link CB is 2 force member. It means we only have force in the link direction. We only have force in the link direction. What next? Okay, let's see the link. Let's see the link AB. Let's see the link AB. This one. Let's see the link AB. Before we apply the equilibrium of force and moment equation, let's just consider the kinematic relationship in the link. Kinematic relationship means we are talking about the velocity analysis and acceleration analysis in the link AB. We have the link AB. At point A, what should be the velocity at point A? What should be the velocity at point A? Point A have the velocity only in the horizontal direction. because this is rotate, and with this current arrangement, it has the right angle here. So VA have only horizontal component. Also for the VB also have the horizontal component. So at point A, we have VA. At point B, we have VB in the horizontal. If the link AB is rotated, if this one is rotated, with omega AB, if this one is rotated with omega AB, the relative velocity of B with respect to A will be in this direction. The relative velocity of B with respect to A. We can compose the relative velocity relationship that velocity of point B is equal to velocity of point A plus B with respect to A. If we consider the direction of the velocity, VB, of course, VB have only horizontal direction. VA also have the horizontal direction. If we have the relative velocity, if we have the omega in AB, the relative velocity should create the vertical relative velocity if omega is non-zero. And the magnitude of VB is 0.2 multiplied by the omega of CB. We don't know the omega of CB, but if we know the omega of CB multiplied by the radius, we can relate it to the velocity of point B in the horizontal direction with the magnitude of 0.2 multiplied by the omega. And how about the velocity of point A? With the same idea, we know omega 0 multiplied by the radius 0.1 omega 0. And the last one, the relative velocity, is the radius and multiplied by the omega 0.3 omega AB. And in y direction, if you compose equation for y direction, for the left hand side is 0, for the right hand side is 0.3 omega AB. So now, in this situation, at the current situation, at this instant, AB doesn't rotate, omega equal to 0. if we check the x direction, if we check the x direction for the equation, 0.2 omega CB should equal to 0.1 omega 0. So now we know omega 0. Oh, no, omega 0. Omega 0 equal to 2. And omega CB is 1/2 omega 0. So omega CB is 1 radian per sec. Is that make sense? Is that make sense for us? We know omega 0, 2 radian per sec. 2 radian per sec. So in this situation, we compute the magnitude of velocity of VA. And in this situation, at this instant, we have the right angle here, and VA only in the horizontal direction. VB also only in the horizontal direction, because if this is constrained at point C, and this length cannot change, the length is a constant radius motion. The velocity at point B here, it can only have the horizontal velocity only also. And VA and VB is equal for the horizontal direction. And yeah, for the horizontal direction, VA will be equal. And we don't have the rotation in the link AB. We don't have the rotation in the link AB. At this moment, it doesn't change the orientation. But I'm not going to say that, hey, when the time pass, point A move to A prime, point B move to maybe B prime. I'm not going to say that. I'm not going to say B prime should be smaller than A prime. I'm not going to say that AB always have 0 omega AB. It just only in this moment omega is 0. Alpha is not 0. It can change the omega when it change the orientation. But at this moment, omega 0 and not rotate, but it still have alpha, and it's gonna change omega to some value, and it's gonna rotate when it change the posture. So for the velocity analysis, we have omega of the link CB. How about the acceleration? The acceleration is it easy? Okay. For acceleration, we still have A and B. We know that the A point travel as a curvilinear in a constant radius. So at A point, we have the tangential acceleration of point A in tangential direction. Acceleration of point A in normal direction. At point A, we have alpha, we have omega, right? So we have tangential as the effect of omega, of alpha. Tangential as the effect of alpha. And we have normal as the effect of the omega. B also has the effect of omega and alpha on it. It's good that we know the current situation. It has the right angle. So we can predict the direction of the normal and tangential direction. The length is fixed. The length is fixed and it have right angle. So at point B, we also have the tangential acceleration and have the normal acceleration. And what if we have alpha of the link AB? I mentioned before that in this current situation, we prove that omega is zero. Omega is zero. But it doesn't mean alpha is zero. But we still don't know what is the value of alpha. But what happened if we have alpha? The alpha will create the relative acceleration. Relative acceleration between B with respect to A in normal direction. If we have alpha, if we have omega, it will create the relative acceleration of point B with respect to A in normal direction. If we have omega, if we have alpha, we will have the relative acceleration of B with respect to A in tangent direction. So to compose the equation for this, we have many terms, but we still keep the same concept of the relative velocity, relative acceleration. But now we know that acceleration at point B, we have acceleration of point B, we have n and t. Acceleration of point B, if we need to form the vector for acceleration of point B, we have n direction, we have t direction. If we form the acceleration of point A, we also have n direction and t direction. N plus t direction. The relative acceleration We also have the relative acceleration in the normal direction. B with respect to A in normal, and B with respect to A in tangential. What is the direction? What is the direction? AN is purely in the upward. AT, okay, AN is purely in the upward, and magnitude, no, ABN, ABN ABN is purely in the vertical direction, upward. Magnitude is omega square R, omega CB square R. R is 0.2. ABT direction to the right hand side, magnitude depend on the alpha of CB multiplied by the radius 0.2. AAN, AAT AAN is upward. Magnitude omega 0 square and radius AAT horizontal. Magnitude is alpha 0, radius the relative acceleration in normal direction. If we consider A point and B point, we have acceleration of B with respect to A in normal direction as a function of the omega AB, as a function of omega AB. So the direction of the normal relative acceleration going to the left hand side with the magnitude of omega square R. Omega is omega of AB square, radius 0.3. The tangential one, A, B with respect to A in tangential direction. The tangential one is point upward with the magnitude of alpha multiplied by radius. Alpha is the alpha of the link AB. Alpha still unknown. Magnitude alpha AB in the upward direction multiplied by the radius 0.3. By the way, in the previous step, we already know that omega AB is 0. Omega AB is 0. Not sure if we try to and we know omega CB, right? Okay, let's check in the y direction. Okay, here, y direction. Let's check in the y direction from this relationship, from this equation. For y direction, the first component is omega CB square 0.2. Omega CB is 1 square multiplied by 0.2. The left-hand side, y direction has only this one. For the right-hand side, 0.1 omega 0 square. Omega 0 is 2, right? 0.1 and 2 square. Yeah, to make it clear for you, I should substitute from, yeah, omega CB is 1 square multiplied by 0.2. Omega 0 is 2 square multiplied by 0.1. And only y direction, we have only alpha AB multiplied by 0.3. Alpha AB multiplied by 0.3. Now we can solve for the alpha. Alpha AB by this is alpha AB by this 0.2, 0.0, 0.4, and 0.3, right? It will be minus. It will be minus. It will be minus. So alpha AB is minus by solving this equation. So what does this mean? So it means that the direction that we assume is incorrect. We assume alpha AB to the counterclockwise direction, but the real direction of alpha AB, it should be positive to the clockwise direction. It should be in the clockwise direction. So in this case, we have the kinematic relationship. We obtain the alpha already. So yeah, we know that for the kinetics of rigid body, we may need to compose the equation for the translation and for the rotation. If we know the information of omega of alpha, it means we have enough information for the computation of the rotation. But how about the rotation? Let's see this link again. AB. The link AB. And when we need to compute the equilibrium of force, we mainly do it about point G. Mass of AB multiplied by G is the force at point G, and CB is two force member. CB is two force member have the force only in the direction of the link, and yeah, maybe BY have only BY, but for AB we cannot say it's two force member. We cannot say it's two force member for OA. OA has the alpha, has the omega. Yeah, it's still not clear that OA is two force member or not. But by here, if you consider this meaning, the crank OA is a driving crank. A drive OA is a driving crank. We should have some input moment applied on the crank OA. So by this consideration, it seems to be, it may not so reasonable if we assume OA to be two force member. But yeah, if you really sure that it's two force member, you can consider it as two force member. But if we still unsure, we don't need to think much. We just write down the possible interaction force. We just write down the possible interaction force, and we will compute the numerical value if it's 0, if it have negative value, and we can get the meaning. From the previous consideration, we know alpha is clockwise direction. Alpha AB is 0.667 in the clockwise direction. So what I'm going to do here is we have A and we have point G. What should be the acceleration? What should be the acceleration of point G? Yeah, A bar vector means the acceleration vector of point G. So A bar acceleration vector of point G. The hint of this is they suggest to use A as a moment center. So yeah, before this, we relate B to A. If we want to know the acceleration vector of point G, we just use the relative acceleration of point A plus the relative acceleration of G with respect to A. Acceleration of A, we have the normal and tangential, AAN, AAT, normal tangential. At point G, at point G, we know that now it's rotated with alpha. It rotates with alpha. So we have acceleration of G with respect to A in tangential, and we have acceleration of G with respect to A in normal direction. But for normal, it depends on omega AB. But yeah, we know that the magnitude of omega AB is 0, but alpha AB is not 0. So AG with respect to A in normal and G with respect to A in tangential direction. AAN upward magnitude omega 0 square R. AAT to the right hand side magnitude alpha 0 R. AG normal omega square R to the left hand side omega AB square. R is the distance here 0.15. The tangential, we know the direction of alpha, so tangential is downward. Magnitude of alpha AB 0.15. So yeah, we know all the numerical value. Omega 0, 2 square 0.1 will be 0.4. 4 multiplied by 0.1. Alpha 0, 0.4. Omega AB 0. Alpha AB multiplied by the radius will be 0.1. No. Yeah, 0.1. So yeah, finally the acceleration vector is 0.4 I plus 0.4 I 0.4 I plus 0.3 J. Here is the acceleration of the point G. Okay, summation of force in X direction equal to mass of AB and AX. Summation of force, we have minus AX only. Minus AX only equal to mass of AB 0.8 kg. Acceleration in X direction 0.4. So AX is minus 0.32 Newton. It means the direction we assume is incorrect. Summation Fy equal to M AY. we have AY positive, BY positive. I'm not sure about the BY. I'm not sure about, yeah, we still don't know the BY direction, but we assume it by this direction first. We assume BY to be positive in upward first, and MG, MAB, G equal to MAB and AY is 0.3. So what next? Next is AY plus BY should equal to MAB 0.8 and 0.3 plus G. Yeah, about 8.0 something. Yeah, we have AY plus BY equal to one constant. We check this again, okay? And for the summation of moment about point A, summation of sorry. We know that the AB have general plane motion. I mean, it's not rotate about a fixed axis. It have the rotation in combination with the translation of the center of gravity. So let's sum the moment about point G. Let's sum the moment about point G equal to I bar alpha of AB, and clockwise is positive. Summation of moment 0.15, 0.15. Uniform slender bar means center of gravity should be in the middle of the bar AB. The point G should be in the middle of the length. So the summation of moment clockwise positive. AY 0.15 AY positive moment. BY negative 0.15 BY negative. Why negative? Because it creates the counterclockwise. I bar, what should be I bar? The bar, yeah, the bar, the slender bar with the rotation about this point. If the bar have length L, I moment of inertia about this point is 1/12 ml square. 1/12 ml square. Rotation about, if the rotation is at the center of the bar, the I bar is 1/12 ml square. So in this case, I bar 1/12 m L square, the total L, okay, square, and alpha of AB positive in the clockwise, and solve the equation. We have AY subtract by BY equal to AY subtract by BY equal to 1/0.15, 1/12, MAB is 0.8, and 0.3 square, and alpha 0.667. Wow. So what is this one? So 1/0.15, 1/12, 0.8, 0.3 square equal to 0.02668. Okay, can we solve the equation? AY and BY. Yeah, we have AY plus BY equal to AY plus BY equal to AY plus BY equal to 8.088, and AY subtract by BY equal to this. So equation 1, equation 2, if we combine these two equations, this means 2 of AY equal to 8.088 plus 0.02668. So AY itself, no, wait. What we need to do for here? What do we want? I'm sorry, we want B. We want BY, right? We want BY, but we obtain AY first. No, just obtain BY. Okay, so 1 subtract by 2. We have 2 BY equal to this. So BY is 4 Newton. BY is 4 Newton. So yeah, in this we need to know the force in BC, but you know that BC is 2 force member. We don't have BX, we don't have CX, we have only CY and BY, the equal in magnitude. And yeah, we solve for the By from here. So to summary, by this type of problem, we may need to begin first with understand the kinematic relationship. If we need to solve for omega, for alpha of the link, we need to consider, we should compute it first. If it simply be obtained, can simply be obtained, omega and alpha is good news. But if it's not easy to do, we need to go back to our previous knowledge on the kinematic relationship, the relative velocity, relative acceleration to obtain the omega, the alpha, and we apply the equilibrium of force, equilibrium of moment equation. For general plane motion, yeah, we select the reference point at the center of gravity of the link. But if the link is one like fixed axis rotation point, we can have the for fixed axis rotation. Yeah, for here we have several. We can summation m about one fixed axis equal to I of that fixed axis alpha, or summation of moment about the G equal to I bar alpha. It depends on the application. For here, general plane motion. For here, maybe fixed axis. So yeah, that's all for this chapter. I will check some example problem and give you in assignment for final exam. Of course, you need to be able to analyze the velocity relationship, the acceleration relationship to obtain omega and alpha. We studied this in the previous chapter, but in this chapter, the top up is to bring this information to the equilibrium equation. So that's all for today. Do you have any question? So I'm gonna stop the recording.
Okay, see you, Achan.